Good day, everyone. Today I'm going to introduce spectroscopy to you and a few of the different techniques, but primarily focus on proton NMR. So a little bit of an overview here. I'm going to go over the briefly just some of the types of spectroscopy, how each technique works, pretty vaguely. I mean, I'll go over a little bit of theory with you. What's actually probed with each one of those techniques, and then kind of break things down for trying to get yourself acquainted with doing NMR. So this is going to be a two-part series. Now, proton NMR is going to deal more with types of connections between different nuclei and telling you what's going to be nearest what, or ways of predicting so based on a frequency. Okay, so chemically distinct hydrogen signals. We'll get into carbon signals in the next segment of this, but for now I just want to get you going with hydrogen. Electronic environment and what that does in terms of influencing a particular frequency. So in other words, if there's more electronegative groups or fewer electronegative groups or more hydrocarbon or aliphatic groups, that's going to determine what kind of frequency a particular signal has. Okay. Next is going to be the chemical shifts. Again, that's related. And then the reference. So how do you know what's a 0 point and what's a high signal versus a low signal, etc. Coupling, split signals, and the N+1 rule, which isn't going to make much sense until we kind of delve into this. And then finally, integration to actually account for how many actual hydrogen signals should be read relative to one another, so based on a ratio, if you will. Okay, so the first thing we want to go over is the electromagnetic spectrum. What regions tell us what? Okay, so the first is going to be UV vis. Of course, very applicable to our own eyes, right? Because we can see things. So this is going to be higher energy light absorption. So your retina, take in, those photo responses, and your brain processes it. UV is going to be a little bit stronger, right? You're not going to stare straight at the sun to, see anything new, right? If anything, it's going to kind of fry your eyeballs. So UV is going to be the highest energy in terms of spectroscopy. So in other words, you're really going to look more at conjugation and what kind of light can pass through in a given system. Okay, so visible is just going to indicate what region about the color wheel where light is emitted. So in other words, if you absorb red, you're going to, get a green, qualitative reading, and vice versa. So if you were to look at a UV vis spectrum, you're going to see that there's going to be an array. So there's going to be, a range of different wavelengths, right? So let's say UV vis is going to be anywhere from, 190 nanometers to all the way to, so lambda, remember, is a wavelength. So 190 all the way up to 850 or something like that. Some of you might have seen this already with some of your biology experiments or what have you. Maybe also some chemistry experiments from Chem 2. Okay, so there may be a little bit of a hump. So small absorption that's over here, so let's say A for absorbance. So this is going to be wavelength, this is going to be absorbance. So anything above 1, of course, is going to be kind of refuted in terms of concentration, because you need some kind of linear response here, and you don't want to go over the point of linearity. Okay, so we'll say right here, this is the highest kind of absorption reading. Say this is at 0.9, something like that. Okay, so pretty high absorption. Now this would be what is referred to as your lambda max. Okay, so in other words, if some kind of analyte that you were probing has so much absorption at these different types of frequencies. So this is a scan, if you will. And this would be sort of the maximum. So you can think of it like a radio, right? So let's say you're one given instance of the country and you're trying to get some kind of signal to listen to NPR or whatever, right? You're waiting and you can scan through all those different frequencies and you're getting a bunch of static. So you can kind of think of this as like static or low noise, and this is like a clear signal. So this is going to be essentially that's the apex or the most of a response you can get at that particular frequency. So let's just say that's 500 nanometers, somewhere in between. I don't know. Okay. So lambda max is typically where you're going to measure your concentration of a particular analyte. Okay, so moving on to infrared. So infrared is going to be lower energy light. So it's going to produce vibrational energy. So if you remember the Passion series from your model of hydrogen, where the principal quantum number n equals 1, n equals 2, n equals 3, all the way to n equals infinity, it's going to be higher and higher energy moving away from the nucleus. Okay, so if you're thinking about functionality, or you're thinking about what kind of functional groups are going to be about a particular analyte, this is going to give you a lot of insight as to what you have, whether it be a ketone, a nitrile, aromatic system, what have you. Okay. It doesn't tell you so much about carbon count and CH and that kind of thing, but there are vibrational energies. So in other words, it's going to be kind of a lower energy overall quanta. Now, one of the most sort of basic or fundamental ways of thinking about infrared is, if let's say you start a fire in the woods, contained in a fire ring, and you're sitting there by the fire, you're not really looking at it for a means of light, although it can kind of illuminate a little bit, but you're really looking at it for more in terms of warmth, and so that vibrational energy translates to heat energy, in other words. So it's going to vibrate, the molecules that you feel on your, or the energy that you feel on your skin, right? Your skin's very sensitive, so it'll pick up on that vibrational energy and will kind of warm you up. Okay. Next is going to be radio waves. So these are the lowest energy light absorption. So this is going to be really low on the electromagnetic spectrum in terms of energy. Remember, the shorter the wavelength, the higher the energy. So this side's UV, this side is more visible, right? So again, think of your eyeballs and their sensitivity. Okay. However, if this is the lowest energy light, that does not mean that it doesn't have a very, very dramatic effect in terms of what you can process about a particular analyte. Okay, so it really is the most powerful, at least conceptually, in elucidating an analyte structure. So that means telling you what kind of connectivity you have, right? If you did an elemental analysis, they would tell you have 6 parts carbon, 5 parts hydrogen, 1 part oxygen, something like that, right? But that's probably not even an existing molecule. I'm just trying to come up with an example here. So really how you're going to be able to tell is by the magnetism, okay? So as NMR instruments, so you may have noticed that we don't have one at Southwest Tennessee Community College. The reason being is because they are very expensive, okay? Something to the tune of $1 million at least. You need a spectroscopist to run it and keep it, shimmed and keep all the programming and everything up to date. Making sure things operate properly, nitrogen to fill everything up, helium to fill things up, probes. The list goes on. It's a very expensive proposition. It's very powerful, but it's very costly. Okay, at least for using an instrument that is very effective in elucidating structure. Now, you're going to have different, so magnets are going to have different resolution. And this will become important when we start talking about coupling, because if you have a good resolution, that means you can distinctly see what those particular splitting patterns are. So you can think of resolution like you see, let's say, an old TV, right? So my mom has this old beater Vizio TV that's flat. Maybe has, it definitely doesn't have 1080 HD or whatever it is. It's really low quality in terms of what you see that's on sale for nowadays. She bought that maybe a decade ago. So it's kind of a dinosaur, right? You look at something in ultra 4K HD, whatever, and you can notice it's just an objective difference, right? So it's no different in terms of magnet resolution. So that's usually measured in megahertz. So let's say 270 megahertz is capital M. Megahertz is type of magnet I used in undergrad, or sorry, not undergrad, but grad school. There were others that I could use that were 500 megahertz, and you can see quite a huge difference, and they're much easier to use. They have auto shims and all kinds of things that can really make the job a whole lot easier. Okay, so just I'm going to get into spin and all that stuff in the next lecture, but for now, let's just go with some of the analysis or things you would expect to see in a particular spectrum. Okay, back to UV vis and how it all works. So UV vis gives some visual response. So again, 400 to 800 nanometers is what you can see with the naked eye. But UV has higher transitions between quanta. So in other words, higher energy transitions. So going from N2 to N1 is going to be higher energy than going from, N4 to N3, right? So as you go from higher to higher quanta, that difference is going to be smaller and smaller. Okay, so as a technique in organic chemistry, it's sort of limited in terms of information to obtain and interpret. Really, it's going to be more of something you would mention in a publication. So it's just kind of, I wouldn't say it's extraneous information. It's good information to have. It's good data to have. But in terms of telling you what that structure is made of, it doesn't really tell you much. Okay, so let's look at infrared. So infrared can provide insight to functionality. Again, tells you what kind of ketones you have, alcohols, amines, right? So they all have, each one of those functional groups has distinctive bands going from lower energy to higher energy. And based on what two nuclei are bound to one another, that can tell you all the difference in the world, how they're bound, right? Whether it being double, triple, single bonds, and the difference between their actual masses, right? So if you have, let's say, a hydrogen and it's really small and it's connected to an oxygen, which is much larger, right? You're going to have so much more of a disparity of weight, right? So it's 1 to 16 atomic mass units. So you can think of, let's say, a golf ball attached to a basketball, right? And just on a slinky bouncing around. It's very sort of chaotic and higher energy versus, let's say, something like carbon that's doubly bound to oxygen, right? That stretch is going to be a little bit shorter in energy because it takes so much more to kind of make these two bonds vibrate. Okay, so it's a little bit more stiff and it's a little bit harder to move if you're using the same energy of photons, i.e. infrared, which is going to be lower than actual visible light. Again, take a look at your electromagnetic spectrum, on the internet or through your old Chem 1 textbook, what have you, and you'll see that those are lower in energy, okay? That doesn't mean that they can't have greater intensity. It's just saying that, you're using a fixed amount of energy probing, okay? So in other words, it's going to affect different functional groups at different frequencies, okay? So these bands that show up are going to show up at higher and lower energies. Okay, so it's great for showing a fingerprint. So, if any of you have ever worked in industry and you see a pure compound and, quality control and quality assurance, they take a look at some of those spectra, those IR spectra, and make sure that everything looks good, right? Something for them to document and make sure that things aren't squirrely and they don't have some impurities in them and what have you. Okay. Now, it's not going to be so sensitive that you're going to see something that's 1% impure or something like that, because that's probably going to be lost in the noise. But you have something that's 50-50 or an entirely different molecule altogether, that fingerprint's really what's going to tell you why it's so different. Okay. Now, moving on to NMR, which is much more powerful. Again, not in terms of actual light energy, but more of what kind of information that it tells you. So this is nucleus specific, so that means you're going to see different ranges of frequencies. So for proton NMR, that's going to be between 0 and let's say 14 ppm, just to be on the safe side. And then carbon NMR is actually going to be anywhere from 14 to, so this is HNMR, between 0 and 14 ppm. And then carbon 13 NMR is going to be from 14 to 250 ppm. So much broader range for carbon. Carbon's actually going to tell you a lot about what you have in terms of a compound, what kind of axis of symmetry you'll have, what kind of functionality you have, etc. So remember, we're dealing with mostly organic compounds here. So that's going to be our analytes. All right. As well as connection to other nuclei and their neighboring nuclei. So something's really electronegative, like a nitro group, that's going to make all the difference in the world in terms of where these hydrogens and carbons end up in their particular ranges. Okay. So is one technique preferred over the other? Is one data piece conclusive? Really, each one of these is one piece of the puzzle for the overall determination, especially if you're trying to make a new compound or ID what something is, as well as mass spectrometry, which is a different technique altogether. Okay. Long and short of it is no. You need more than one piece of data. You need something that's both reactants and products, just to see, did I even, maybe things change colored, but did a reaction actually occur? You don't know. So, again, it's not really the lazy way to go about things. You need to get multiple data points to say, okay, all this points to a ketone, or all this points to an aldehyde, or whatever. Okay. Okay, so let's take a look back at just some structures here and just see if we can make some kind of prediction. Okay. So there are 3 or 4 different pieces of criteria here that I'm going to have you focus on. Now the first, so this is proton NMR, so that means proton's just short for, HNMR. So you have hydrogen here, hydrogen here, hydrogen here. There's also 2 hydrogens on the other side of the ring. This is para-nitrophenol. Okay. Now, there's going to be an axis of symmetry about this particular ring, right? So in other words, this side is going to look the same as this side. I know that things kind of look asymmetric by how things are written, but remember that this can rotate about, and this is just going to be two oxygens sticking on either side. So in other words, it's going to be, there's going to be an axis of symmetry here. So how many different hydrogens given their electron environment? Well, we have a total of 1, 2, 3, 4, 5. However, the total amount of signals, if these are equal in terms of their electronic environment, remember that these double bonds are constantly going to be in motion, okay? They're going to be an electric current. So and that's going to affect a frequency, when we'll get into that in a minute. But in terms of what kind of signals you're going to see, these two are going to average out to be in the same region, okay? Now, are they going to be bigger or smaller in terms of size, or how big or small those peaks are? We'll see. Okay, now, so we would say that this is one signal because there's nothing else like it. These two signals, or these two hydrogens, are going to be about the same signal, right? They're going to show up in the same frequency. And then these are also going to show up at the same frequency. Why are they going to be different? Well, because these hydrogens are just adjacent to this junction here where NO2 is. And these two hydrogens above are going to be nearest this junction where the OH group is. So in other words, we're going to have a total of 3 signals from an axis of symmetry. Okay, so again, these two are going to average out together. These two are going to average out together. And this one is just a lone wolf. Okay. All right, so these signals will appear at different frequencies. Okay, and I will get into the frequencies and parts per million, chemical shifts, whatever have you, in a minute. Okay, so let's think of another example here about 2 methylhexanone, hexane 3-one rather. So 3 positions where the carbonyl is, 2 positions where the methyl is. Okay, we have a total of 14 hydrogens. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right? So we need to fill out our octet, at least from sort of a mental standpoint and from a line structure, because we don't have all the time in the world to draw hydrogens out, right? Okay, so a total of 14. How many different signals? Well, here's the catch. There's just a sole electron here, but there's 3 electrons, one hydrogen here. There's going to be 3 hydrogens here and 3 hydrogens here. These are going to be equal in frequency because they have the same relationship, right, with respect to everything else that's around them. So in other words, that's going to be all one signal. Even though this is 6 hydrogens, one signal. Okay. And then this is going to be a lone hydrogen itself, so that's going to be one signal. Okay. And then we're going to have 2 hydrogens over here. This is going to be a methylene group. This is all going to be one signal. So in other words, one place in which that one frequency in which these hydrogens will appear. Again, on a spectrum. Okay? So spectroscopy means that you have some kind of spectrum to interpret. Okay, so this isn't just something that you kind of come up with in thin air. No, things get processed, things get shown through a graph, if you will. And, the x-axis is going to tell you where these frequencies appear from 0 to 14 ppm. Okay, and then the y-axis is just going to tell you the intensity of the signal. Okay, so they should be proportional, and I'll get into that in a minute. Okay, so this is another signal. Are these two the same? No, because this one's right next to a methyl group. This one's right next to a carbonyl. So in other words, these are 2 chemically distinct signals. Okay, and then last here, this is going to be 3 hydrogens, but it's still going to be one signal. So for a total count of signals, 1, 2, 3, 4, 5. Okay, so a total of 5 signals. But there is no axis of symmetry. The only thing that's symmetric here is just these 2 methyl groups that are attached or bound to the same carbon. Okay. All right. So this is a common organic solvent. So N,N-dimethylformamide. So this is an aprotic solvent. So there are a total of 7 hydrogens, one being from this from the other side of this amide. This is a tertiary amide. So we have 1, 2, 3, 4, 5, 6, 7 total hydrogens. How many different signals? Okay. So that lone pair is going to kind of shift things around, but remember that also it can conjugate with this oxygen, right? So it's going to always be in conjugated form, moving back and forth. So it's somewhat resonance stabilized. But 3 hydrogens here, 3 hydrogens here, they're going to average out to be about the same signal, okay? So it's going to be 1, 2 signals. All right, so what I just went over here was all chemically distinct hydrogens, okay? So even though there are 2, let's say, repeats of 1, 2, that's going to show up more in terms of integration, not frequency or where things are going to be within that range of frequencies, okay? So what happens to the specific hydrogen signal when an electronegative group is adjacent or neighboring is what is referred to as deshielded, okay? So in other words, there is no, there's nothing to keep those frequencies, sort of in a lower state, if you will. So what the magnet's going to do is actually going to change the sign or the direction of where those particular singlets are going to be. So hydrogen is just going to have 1 electron, right? That it's going to share with another electron to be covalently bound. When that thing flips, it's going to go into higher energy and then precess and fall down. And we'll get into that a little bit more. But an electronegative group is going to actually affect that frequency quite considerably. Okay. So 0 ppm, again, is going to be the reference. You need some 0 point. So where tetramethylsilanes, methyl group, methyl hydrogens appear. So it's just going to be one big spike right there at 0 ppm. And this is actually placed in every single NMR solvent that you would use to interpret whatever type of analyte you're using. Okay, so TMS is short for tetramethylsilane, is off by plus or minus whatever ppm. Then all signals from the analyte that you're interpreting must be offset by that magnitude, whether it be plus or minus, okay? So if you're seeing something that's 4.2 ppm and this is at negative 0.2 ppm, then you're gonna have to offset that to 4 for the actual signal, right? 4 ppm for whatever you're looking at. Okay, so hydrogens are in everything. So how are you going to be able to determine that from, let's say, the solvent? Well, the solvent is actually going to be using a deuterated, I don't make the terminology up. So let's say a very common solvent is CdCl3. Okay, so that's what is referred to as deuterated chloroform. You think of chloroform as CHCl3. Okay, so in other words, if you have a heavy isotope of hydrogen, it's not going to show up on that particular spectrum. Okay, so back to the signal identity in the electron environment. Okay, let's take a look now. So this is another sort of lengths. We're going to be looking at 2-methyl 1-hexane 3-one. Okay, so now we have the 2 signals that are going to average out together. Again, that's going to give you 6 hydrogens in total. that's going to show up around 1.11 ppm, so a little bit to the left of where that 0 reference point is for TMS. Okay, that methine hydrogen that's right here is actually going to be even higher. So this is what's referred to as being de-shielded. Now notice that adjacent to that you have a CO double bond. That CO double bond is going to be highly electronegative. So in other words, that's going to remove some electron density away from this hydrogen, and it's going to de-shield that spin, right? So then you have on the opposite end, you have something that's just disubs. You have a secondary carbon here. So this is a tertiary carbon. This is a secondary carbon. And that hydrogen that's attached, those two hydrogens actually, rather, that are attached right here, are going to be at 2.18. So it's still de-shielded from the CO double bond, but a little bit less so. The reason being is that if these carbons are directly attached to this carbon where the hydrogen is, those carbons are slightly more electronegative than hydrogen itself. So that's why you see sort of an appreciable difference between 2.58 and 2.18. Okay, so instead of having two aliphatic carbons attached, you just have one here. Okay, so the next is gonna, so it's gonna drop down precipitously as you jump from one bond to the next. This is gonna be 1.3 ppm, and then at the edge, this should be somewhere between 0.9 and 1 ppm. So this is gonna be lower. This is what is referred to as being more shielded, okay? So this is going to be closer towards 0 ppm. Notice how shielded this is, because tetramethylsilane is going to look like this. And the reason why they use silane as the central element is because this is so much less electronegative than carbon, right? It's the next step down. It's isoelectronic to carbon, but it's going to be less electronegative. Remember, the trend for electronegativity on the periodic table goes up and to the right, generally increasing, right? Okay, so what can you say about the chemical shift of each hydrogen assignment? What are the higher values nearest? The lower values, again, the highest values are going to be nearest the electronegative groups. Okay, and the lower values are going to be in more kind of hydrocarbon dense or aliphatic. So in other words, you can think of all these hydrogens that are bunched up near one another. You're thinking about a big electron cloud as opposed to this sort of linear construct that's just in lines. It's going to space out, and it's going to have some sense of solidarity, right? Those electrons are going to want to have similar energy. So that's why there's what is referred to as a shielding effect. Okay, so now let's look at paranitrophenol again. Okay, so I flipped it upside down here. Forgive me. But same principles and everything are going to be applied here. So notice how that hydrogen's directly attached to oxygen, 11.1 ppm. Whoa, buddy, that's, you know, a whole order of magnitude higher than what we see right there when it's just attached to a carbon, right? Now, not only is this electronegative, it's bound to this electronegative oxygen, this oxygen can also what? Conjugate with the rest of this ring system, even with that NO2. So in other words, it's going to be very much higher in frequency, okay? So very de-shielded, this hydrogen. Okay, so the electron density is going to be way over on this side. Okay, and this is something that will carry on into the next semester should you continue. You'll see how this makes a whole lot more sense. Okay, so 6.96 ppm. So this is nearest the OH group. Remember, we have 1, 2, 3 signals. Okay, so these two average out together at their respective frequencies. So this is 8.14. Notice how this is right next to NO2. Okay, now a little bit of a concept check here, and this is something that I'll get into in the next lecture as well, and at least involving spectroscopy. This is going to constantly resonate, right? This is a benzene ring. It has some an electron withdrawing group, strongly electron withdrawing here. It's very electronegative. This is electron donating because it has a lone pair to feed in, or actually two lone pairs to feed in. Only one's going to go in. Okay, so with that said, look how much of a difference it is relative to, so this is carbon and hydrogen, right? So you think, well, can't be that bad. Why is it so high? Why is it so deshielded? Well, here's the reason. Is that since we have that resonance here, and these electrons are constantly cycling about, remember that a current, for those of you that have taken physics, a current, per the right-hand rule, is actually going to generate a magnetic field within itself. So in other words, this magnetic field is going to basically create sort of like a solenoid, if you will, in terms of direction, and that will constantly go in and out of the ring. So what that's going to do for the hydrogens that are sticking outside is actually going to deshield, right? Because you have these pi bonds here, and this is already electronegative or electron withdrawing. Okay. So this is what the induced magnetic field, what I was just referring to, is what is called anisotropy. So we'll see those effects in the next lecture when we get into carbon NMR as well. Okay, so the next thing we're going to go over is splitting signals. Okay. So we'll take a closer look at this particular compound. So this would be 2-acetyl 5-ethyl pyrimidine. Okay. So is there an axis of symmetry? Yes. Right, and just go straight down here. Okay, this will be 50-50 probability on either side, so that doesn't matter. This has the ability to rotate, so that doesn't matter. But these are both going to be in a fixed pair position relative to one another. Okay, so how many total hydrogens do you have? You have a terminal methyl group right here, so that's going to be 3. You don't have anything here. You don't have anything here at the junction. You don't have anything about either nitrogens, right? So we just have lone pairs about both of these nitrogens. Okay, and then we have a hydrogen here and a hydrogen here. Are they the same in terms of frequency? Yes, they are. That's why I made that particular note. Okay, and then finally we have an ethyl group that's sticking off here. This is going to be somewhere in the neighborhood of 2.1 ppm. Okay, so that methylene group just adjacent to the ring is going to be deshielded some. And then this methyl, it's again going to be terminal on the top. That's going to be about 1.2 ppm. So slightly deshielded from what is expected for aliphatic, which is about 0.9. Okay, so with that said, how many total hydrogens? 3, 4, 5, 6, 7, 8, 9, 10. So a total of 10 hydrogens. So that would what you would expect to see relative if you were to assign, let's say, this particular signal 2 hydrogens. Okay. So, these would all, again, show up at radically different frequencies. So, you'll see 4 total distinct signals. 1, 2, 3, 4. Okay. So the chemical shifts of those signals I've already assigned. Okay. So based on, again, their electronic environment, you're going to see a difference in terms of frequency. Okay. So how many hydrogens are 3 or fewer bonds removed from nearby hydrogens. Okay, so let's think about now these methyl hydrogens to these methylene hydrogens. How many bonds are removed? 1, 2, 3. Okay, so that means they're close enough to where those electrons that are whizzing about the CH and CH here have the ability to couple with one another. Okay, so in other words, that's kind of a solidarity effect. That's why you see that they have lower, what do you call that? Frequencies. Okay, so if they have lower frequencies relative to what you see here, then there's sort of, again, an act of solidarity or shielding of those electron nuclei. Okay, now if we think of 8.6 ppm over here, these are going to be how far removed. We're going to be 1, 2, 3, 4 bonds away from the next hydrogen, right? So, or 1, 2, 3, 4 bonds away from that hydrogen on the opposite end. So in other words, you're not going to see any coupling, okay? At least in terms of first order coupling, that's all we're thinking about. Okay, so in other words, these are going to be singlets. Okay, so no splitting, right? So the split signals you're going to see, so CH2, again above, there are going to be 3 bonds removed from methyl hydrogens, so CH3 hydrogens, okay? Conversely, CH3 above, again, that aliphatic, is going to be 3 removed from the CH2. So it's some reciprocity between the two in terms of coupling. Of course, it takes 2 to couple, right? Or even more, and we'll see that in a little bit. Okay, so let's think about the unsplit signal. So this is going to be split, and this is going to be, these 2 signals are going to be unsplit. Okay, so we forgot to talk about this, or at least I forgot to talk about this methyl here. So this can't couple with anything because it's 1, 2, 3, 4, 5, 6 bonds away. Forget it. It's going to stay by itself. And, those 3 hydrogens, again, are going to all average out to the same frequency. So it's going to be triple in intensity that you see for, or it's going to be a 3-to-2 ratio for what you see here. It's going to be a 3-to-2 ratio for what you see at this carbon. And then a 1-to-1 ratio that you're going to see between these two. However, these 2 signals are going to look different. They're going to appear different. Because this one, if it's standalone and isn't split by anything, is just going to be a singlet. So it's just going to be one sharp peak sticking up and then coming right back down. Okay. So again, CH3 below is going to be 6 removed from the ring hydrogens, which is the nearest. And then ring hydrogens are going to be 4 removed from the CH2 and the other ring hydrogen, like I pointed out earlier. Okay. So in other words, you're going to see a singlet of 2 hydrogens for the ring, and then 3 hydrogens for integrating to 2 and 3 respectively. Okay, so this is where the n+1 rule comes in. The 1 is going to be the actual singlet where one particular hydrogen signal is going to occur. However many times it's split is based on how many hydrogens that are chemically distinct from it are splitting it up. So in other words, the CH2 signal that you see up here, we treat that standalone, if there was nothing else here to split it up, as just 1, right? But seeing as we have 3 hydrogens over here, it's going to split it from 1 to 4, okay? So now, that's going to appear as a quartet. So a quartet is going to look something like this. So it's going to be like 1, intensity to 3 to 3 to 1 intensity. And this is all going to follow Pascal's triangle. You'll be able to see that in your text. Okay, so text is really going to be reference, it's sort of going to be more coloring for what I'm talking about here. Here's more of the meat and potatoes as to what you're going to see, and that'll tell you a little bit more as to why. Okay. Now, so it's going to be a 1 to 3 to 3 to 1 ratio of intensity. So that means, will this, if you were to integrate this, integration looks like this particular signal. For that, you would see 2 because there are 2 hydrogens. So you would just put 2 right there. And that's how you would normalize the signal, because the instrument doesn't know exactly how many hydrogens you have, right? It's just going to tell you the intensity of each signal, and that's it. You have to normalize it yourself. Okay, so the next one is CH3. So again, that's the methyl that's going to be above, that's going to be coupled to CH2 next to it. So that signal appearance, again, these are all going to average out to being the same signal, right? That same singlet. But when you have 2 hydrogens that are adjacent to it, that are coupled, it's going to split it into 3. So in other words, 1 and then plus 2. 2 is going to be your n value in the n plus 1 rule. Likewise, these 3 are going to be the n value for the previous signal I was discussing. So in other words, for the CH3, typically you're going to see a triplet if it's split by something. So it's going to be 1, 2, 1 ratio of intensity. So in other words, it's going to look like Raphael Psi in Ninja Turtles, right? Okay, now split signals have coupled hydrogens that are chemically distinct, right? So in other words, these 2 hydrogens that you see right here are not like these 3 hydrogens that you see right here, and vice versa. Okay, so that's where the coupling and splitting comes in. If you have the same signals, again, they're gonna all average out on the same frequency and not split one another apart. We'll go over other examples with splitting here. So here's another, re-examining 2-methyl hexane 3-one, again through the lens of splitting. So we have 1, 2, 3, 4, 5, 6. Okay, so that's going to be hydrogen A. Again, 6 hydrogens. Okay, so that's going to be the integration or relative amount. Okay, so, and then that's going to be split by hydrogen B, which is right here. Okay, so the 1 from n plus 1 rule is going to be right here. Doesn't matter the count, okay? What's going to be relevant is how many hydrogens are going to be splitting it. It's just going to be this 1 because, again, that hydrogen is 3 bonds removed. So it's going to split, and that splitting is going to be a doublet. Good Lord, can I write today? Doublet. There we go. There are my initials. Okay, so in other words, that doublet is going to look like so. So far spaced apart from one another. So it's going to look like the same, signal, just close enough to where that sort of valley that's in between the 2 peaks is going to be slightly higher than the actual baseline. So you're going to see a baseline where things are 0, like a baseline should. And you're going to see them at equal intensity or relatively equal intensity. Okay, moving on. So hydrogen B split by hydrogen A. Remember, there's a reciprocity there. This is going to be now not a doublet, but a septet. So in a total of 1, 2, 3, 4, 5, 6 for your n value, plus 1 to give you 7. Okay, so that intensity, and you would really report this more as a multiplet. Whew, man. The Smithsonian is going to come out of quarantine and put that in there. Okay. So let's move on to C. True work of art right there. So septet. Okay, for those of you that know me, you know I'm being total smart aleck there. But okay, so hydrogen C split by hydrogen D. Okay, so you have an integration. Let's go back to integration here. So HB is just going to be one hydrogen. Okay, so back there. Now on to C. HC is going to be consisting of two hydrogens, again at the same frequency. It's going to be split by by hydrogen D, which that splitting is going to be a triplet. Okay, so again, two hydrogens representing the N, one signal, that's going to be one, total of three. So 1, 2, 1, and that's going to be your triplet. And there's actually a figure in your text that shows, you know, the average or probability of the electrons going up or down. So it's going to be like this. And that kind of explains it pretty well in terms of how splitting occurs. Okay, D. So we have 2 here, we have 3 here, and then we have just the one signal from, again, 1 on the N+1 rule. So we have a total of 5 hydrogens that are both chemically distinct. Now, are we going to get a sextet, which is 6? No, not necessarily. Get your mind out of the gutter. It is actually going to be a quartet of triplets or a triplet of quartets. So it looks something like that. Weird, right? So you would just really say multiplet. That says multiplet. All right. Then lastly, the easy one. So E on the end there, that's going to be a methyl hydrogen that, again, those 3 are going to be the same range, or the same frequency, but they're going to be split by D, which is going to be a count of 2. So I mean, N equals 2 plus 1, you're going to get a triplet. Okay, triplet. Okay. And let's go back and cover all of our tracks in terms of integration here. So 6 hydrogens for A, 1 hydrogen for B, 2 hydrogens for C, 2 hydrogens for D, and 3 hydrogens for E. Okay, so to wrap things up, I'll give you these few to practice. So I will pause here. So first problem is just going to be signal count. So A, D, G, and I. The next problem, which is going to be N+1, which is what we just did for splitting. So the N+1 rule. Problem 16.58 on page 831. A, C, E, and F. And then the last is integration, problem 16.55 on page 381. So why don't you give those a shot, and I'll be right back with the answers. So pause for about 10-15 minutes and give that a whirl. Okay, so for signal count, remember there's an axis of symmetry right here. So in other words, these 2 signals are going to cancel out. These 2 signals are going to cancel out. All 4 of these signals are going to cancel out, or sorry, not cancel out, but align at the same frequency. And these 2 are going to align at the same frequency. So you're going to have a total of 2 signals. Okay. Notice how there are different electron environments here. So this is an ester group, but it's not symmetric. All right, so we have two different ethyl groups on either side, but they're all going to have different electron environments. So this one's directly attached to C double bond O. This one's attached to an ester oxygen. So in other words, you're going to have 1, 2, 3, 4 hydrogen signals. Okay, so we're not really concerned with where they'll appear for right now. You can take a look at the chemical shift chart in your text and sort of approximate those. Okay, and then this third example, G, so we have one hydrogen here. We have two hydrogens here that are adjacent to this juncture, but they're going to have different electron environments because this one's situated between OH and Br. Okay, so it's going to be different from what's up here. So we're going to have 1, 2, 3. This is, again, you see an inequality here between OH and Br. So there's going to be different electronegativity distributed about this ring, a little bit more toward the oxygen. So this is going to be chemically distinct as well. This is going to be closest to bromine without having that OH group. So this is going to be different too. So a total of 1, 2, 3, 4, 5 signals. Okay, moving on. We do have an axis of symmetry about this ring, right? Because it's monosubstituted. So it means there's just one branch coming off or one juncture. So 1, 2, 3 signals. Okay, so these two average out, but this one's lone and different. So with that said, there's a total of 3 about the ring, 1 to 2 to 2 in terms of integration. Then we have 1 here, and then we have 1 here, and then we have 1 here, because all of these are going to be chemically equivalent. So a total of 9 hydrogens here are chemically equivalent. So in total, we're going to have 1, 2, 3, 4, 5, 6. Okay, so going back to this 1,4 diol benzene ring, our para relationship, we have splitting. So are these two going to split? No, because they're identical, right? In terms of chemical identity, they're the same. So how many bonds removed from this hydrogen? 1, 2, 3, 4. So these aren't going to split. So in other words, this is going to be a broad singlet, because remember, this can hydrogen bond either as a donor or an acceptor with another adjacent molecule or nearby molecule. Okay, so you're really going to have singlets. So in other words, there's going to be no splitting. That N is going to be 0 for both instances. So you're going to have 2 singlets. Okay. And then for the second molecule, which is the same as what you had here in the signal identity. So you have a methyl group, which is going to be split by 2 hydrogens. So that means N equals 2, N equals 2 plus 1. So that's going to be a triplet. Okay, and then this hydrogen is going to be split by 3 hydrogens that are chemically distinct from it. So this would be a quartet. Okay. All right, and then we have a chicken foot on the end here. So this is 1, 2, 3, 4 bonds removed from the next hydrogen that's chemically distinct from it. So in other words, this is going to be a singlet accounting for 9 hydrogens. Okay, and then this is not going to be split by anything over here. Again, this is a singlet, so therefore it doesn't couple to anything. But it is going to couple to this hydrogen, these two hydrogens you see right here. So in other words, this is going to be a triplet because you have N equals 2 between these two methylene or hydrogens, and then this one signal. Okay, so remember, there's still 2 here, but it's just going to be, so this should be a triplet, and this should be a triplet, and they're going to be reciprocal among one another. But triplet for the sake of the answer. Okay, and the last one here, so we have, they didn't distinguish, but this is going to be a multiplet, okay, because this is what is referred to as being diastereotopic. So one hydrogen is going to stick out up above just where these two chloro groups are sticking up, right? So in other words, they're going to be cis to one another. So this hydrogen is going to be in the same region or chemical sort of electron cloud, if you will. And this is going to be below. So they're going to be somewhere near in signal or in terms of frequency, but it's going to be a multiplet. And you're going to see second order splitting. All right, so for integration, problem 16.55 on page 831. Okay, so we have 6 hydrogens that are, again, there's going to be an axis of symmetry here. So 6 hydrogens about a methyl group. 1, 2, 3, 4 hydrogens about the ring. And there's an axis of symmetry here vertically as well as horizontally. So in other words, it's going to be a 3 to 2 relationship, 6 to 4, 3 to 2. Lowest common denominator of methyl to ring. Okay, and then the tri-substituted benzene ring with all methyl groups, excuse me. That's going to be, and this is a 1, 3, 5 relationship. So you're going to have 1, 2, 3 ring hydrogens, and then 3, 6, 9 methyl hydrogens. So divisible by 3, so it's going to be a 3 to 1 relationship of methyl to ring. Hope that was helpful, insightful, what have you. We'll go over more later on in the semester when you're just about ready to gear up for your final. Have a good one. Take it easy.